In the previous lesson, we designed a simple convolutional neural network architecture that can be trained to recognize handwritten digits in the MNIST dataset. This CNN consists of two convolutional layers, each followed by a max pooling layer. The output of the second max pooling layer is flattened into a column vector and passed to a fully connected part of the CNN that determines the probabilities that the image shows each of the 10 digits from 0 to 9. The architecture of this CNN was discussed in detail in the last slide of the previous lesson. In this lesson, we will implement this architecture from scratch using PyTorch. The first thing we need to do is loading and preprocessing the MNIST dataset. We can import it from the datasets module in the Torch Vision library. In PyTorch, datasets need to be packaged into data loader objects that manage loading and iterating over elements in a dataset. This class is available as data loader in the torch.utils.data module. We separately load the training and test sets of the MNIST dataset by setting the parameter train of datasets.mnist to either true or false. Each loaded training or test sample is then converted to a PyTorch tensor and normalized. For training, we use a batch size of 64 randomly selected images from the training set of the MNIST dataset, shuffle equals true. For testing, we use a batch size of 1000 randomly selected images from the test set of the MNIST dataset. Let's use Matplotlib to visualize 25 samples of the training data. Training samples consist of images of digits. We unwrap them into the variable example underscore data and labels that contain the ground truth of what those digits are. We unwrap them into the variable example underscore targets. Then we visualize the first 25 training samples. Notice that in the PyTorch tensors that contain the image data, the first dimension is the channel number, followed by the width and the height of the image. For visualization, however, we need to reorder the dimensions so that we have width, then height, then channel number. We accomplish this operation using the permute method with the desired order of dimensions in the original tensor as parameters. We can see that there is considerable variability in the images of digits that correspond to the same label. We will now define a new class, net, that will contain the architecture of our convolutional neural network. This class will inherit from the parent class nn.module, just like any other custom PyTorch class that defines a neural network architecture. And just like with any PyTorch class like that, it will contain two required methods: the constructor, double underscore init double underscore, and forward. The double underscore init double underscore method will initialize all the parameters that are defined for the class. In this case, primarily the individual layers of the neural network. The forward method will define how data is passed through the neural network. The double underscore init double underscore method takes only the self parameter. This method first initializes all parameters of the parent class by running the constructor method of the parent class. Then it defines the first convolutional layer in our CNN, self.cnn1. A convolutional layer is defined as an instance of the conv2d class that is contained in the nn module of PyTorch. We set the parameters of the layer according to the schematic in the first slide of this lesson. The number of input channels is set to 1 because our input is a grayscale image. The number of output channels is set to 32 because we want to use 32 filters for this layer. The kernel size is set to 3, the stride is set to 1, and the padding is set to 1. A convolutional layer with such parameters will produce a same convolution. No activation function is applied in the first convolutional layer that we just defined. Therefore, we define the activation function for it, self.relu1, separately as a relu function. The first max pooling layer, self.maxpool1, is defined as an instance of the maxpool2d class that is contained in the NN module of PyTorch as well. We only need to set one parameter for the max pooling layer, the kernel size, because by default, the stride is chosen to be the same as the kernel size. Note that no activation function is necessary for pooling layers. The second convolutional and second max pooling layer are defined analogously to the first convolutional and first max pooling layer. The only difference is that for the second convolutional layer, the input image is the output of the first max pooling layer that has 32 channels. And the number of output features is set to 64 because we want to use 64 filters in this layer. The first fully connected layer is defined in the standard way for defining fully connected layers in PyTorch using the linear class that is contained in the NN module. As we established in the final slide of the previous lesson, the number of inputs for the first fully connected layer is 3136. The number of elements in the flattened output from the second max pooling layer. The number of outputs for the first fully connected layer is 128, the same as the number of inputs for the second fully connected layer. The activation function for this layer is relu. The second fully connected layer is defined similarly with 128 inputs and 10 outputs. We use a softmax activation function here so that the outputs of this layer can be interpreted as the probabilities that the image is of each of the 10 digits from 0 to 9. The forward method of our CNN class definition sets the sequence in which the data passes through the neural network. Therefore, in addition to the self parameter, it also takes a second parameter, our data sample, x. Each data sample is first passed to the first convolutional layer, self.cnn1. The output from that layer is assigned to the variable out that is then passed to a relu function and reassigned with the result of applying that function. The output from the first relu function is then passed on to the first max pooling layer, and so on, layer by layer throughout the network architectures that we have chosen and the layers for which we have defined in the double underscore and a double underscore constructor method. The output of the second max pooling layer is flattened, that is reshaped to a column vector with the number of rows equal to the number of elements in the output of the second max pooling layer. The resulting vector is then passed to the fully connected part of the CNN. The forward method returns the output of the softmax classifier. As is generally the case with PyTorch, we only need to define the forward propagation, and back propagation is going to be performed under the hood during training. It is now time to train our neural network. First, we initialize our model, network, as an instance of the net class that we just defined. For training, we will use the stochastic gradient descent optimizer, which is defined by the SGD class in the Optim module of PyTorch. We will create an instance of the SGD optimizer with the following parameters. Network.parameters invokes a method that is defined for the parent class of net, nn.module. This method returns the model's parameters that will be trained. LR is the learning rate. Here it is set to 0.01. And momentum is the momentum for stochastic gradient descent. Here it is set to 0.5. We will train the model for 5 epochs, saving its parameters after every 10 batches to a specified path. Because we have a multi-class classification problem, we will use the cross entropy as our loss function. Let's define the function train for training our CNN for one epoch. First, we set the model to training mode using the train method that is defined for the parent class of net, nn.module. Then, we iterate over all batches in the data underscore train data loader that we created. For each new batch, we reset gradients of parameters to 0, perform a forward pass on the data, calculate the loss function, perform a backward pass to calculate the parameter gradients, and then adjust the parameters of the model using these calculated gradients. If we have run training for 10 batches since the last save, we also save the model and optimize the parameters. Once we have trained our model on all batches, we print out the training loss and the completed epoch of training. The parameter epoch that is passed to the train function is just the epoch number and is only used in this print statement. Let's define the function test for testing our CNN. First, we set the model to evaluation mode using the eval method that is defined for the parent class of net, nn.module. Because for testing we don't need to perform backpropagation, we disable gradient calculation using torch.nograd. Then we iterate over all batches in the data underscore test data loader that we created. For each new batch, we perform a forward pass on the data, calculate the loss function, and compare the model's prediction to labels for the test set that defines the ground truth. We then print out the test loss as well as the accuracy for the test set. We now train our model for 5 epochs, printing out the training and test losses as well as the test accuracy after each epoch. The freshly initialized model with random weights has an accuracy of about 10%, as expected for randomly guessing one of 10 possible classes. After the first epoch, the test accuracy goes up to 91%, and after 5 epochs, it goes up to nearly 97%. The training and test losses remain similar throughout training, indicating that we are not overfitting our model significantly. To summarize, in this lesson, we have defined and trained a simple convolutional neural network in PyTorch that is able to identify handwritten digits with 97% accuracy. Any other CNN in PyTorch can be defined and trained similarly.